viewers. Where are my viewers? Viewers, where are you? Okay. Let's do something. Time to do something about this analog pre-processing. What it is, why it's needed. Who are these people? Okay. What's here? Couple of objects. I have small demo here. Oh, what I get? Generator. Here's my generator. It's a very good and stable generator. Its distortion rate is less than 1 in 1,000. Actually, can be better. Can perform with distortion rate 1 in 10,000. It's a good generator for acoustics. Heavy, but it's not a problem. So my generator supplies me with ideal harmonic signal, 10 kilohertz. Oh. Okay. I have a demo here. Good harmonic signal generator supplying 10 kilohertz to my scope. And today thematics is analog preprocessing. What is analog preprocessing? And why I need 10 kilohertz harmonic signal? Oh, 10 kilohertz harmonic signal and digital scope. What is this? I'm changing time scale. Actually, I'm changing sampling rate. Till this moment, everything appears to be fine. Still fine. Oh, something starts to happen. Oh, I love this one. I love this one. Oh, no period form. You see what my scope is showing? Oh, 4 hertz. Is it 4 hertz signal? This one is better. 4 hertz. Sine with frequency 4 hertz. Actually, did I change anything in input signal? No. Here it is, 10 kilohertz, ideal harmonic signal. I can add another scope. I'm only playing with sampling rate. And you see what's going on? Scope thinks what it's a 4 hertz signal. I can shift frequency a bit. In opposite direction. 1.6 hertz signal. Scope sees something absolutely different from reality. I'm introducing tiny shift in frequency. Pitch. 0. This is instead of 10 kilohertz. On different frequencies, on different sampling rate. You get something like this. While in reality, it's simple 10 kilohertz harmonic signals. One signal. What's going on? We see one of the basic problem of digital signal processing. Name for it aliasing. this effect is called aliasing effect. What's going on? Look. For example, good harmonic signal. I'm doing samples to perform digital processing. These are points in my computer or my digital system. These are points, this is a table of values. So, tau sampling interval, and red line is my signal as I tau. When, for example, this 1, 2, 3, 4, and so on. I is a measurement, number of measurement inside measurement table. Here I draw normal sampling. Normal sampling when I have enough points inside observation window to represent signal. What can happen? What if sampling rate is too low? At some moment we will get something like this. Here is signal to observe. Measurements. Let's say 1, 2, 3, 4, and so on. Here, sampling interval is high when the repetition period of observed signal. What will I see? If I create something like very slowly, like a stroboscope, I will get something like this. It isn't original signal. It's this red line consisting of multiple points from multiple periods. Okay. How to say common sense should tell me what minimorum of sampling rate should be in such a way that I will have at last 2 points per period. Oh. It's a minimorum, so tau should not exceed, should be less or equal half of period. Yeah? At last 2 points per period to somehow understand what's going on. And this is not all. At this moment I speak on ideal harmonic signal containing only one frequency. If my signal contains frequencies from omega minimum to omega maximum, what should be a sampling rate. I need at last two measurements for highest frequency of my signal. So if omega is double P divided by mean, this is period of top harmonic component of my signal. What I can say? I can say what tau sampling interval or period of sampling equal to 1 divided by f. D, it's a sampling frequency. So sampling period should be at last equal to what? And, half of the T max, T mean, meaning what frequency of sampling, discretization, frequency and sampling should be at last twice and f maximum. Sampling frequency to represent original our process signal correctly should be at last twice the maximum frequency of our signal, maximum frequency component of our process signal. Name for this, Nyquist frequency. Nyquist frequency. Idea of Nyquist frequency, again, sampling frequency of our digital system should be at last twice of maximum frequency in observed signal. Or you get rubbish instead of results. What this means? You have voltage, you have current at the input. At some point you need to do one thing. You have device with limited calculus capability, device with limited sampling rate. You need to limit spectrum of your signals. Here is the borderline. It's a 1/2 of sampling frequency of your device. Spectrum of signals you observe should not contain components above half of the sampling frequency before you can even start digital processing, or you will get absolutely rubbish. You will get 400 millihertz instead of 10 kilohertz. So, and now, before you can perform digital processing of your signals, you should, it's a must, perform an analog preprocessing, cutting off components above Nyquist frequency. I can draw it in red. It's a Nyquist frequency, half of sampling frequency. Now, looking deeper. And what's mean deeper? you need to understand what? Spectrum of your signal. Frequency components of your signal. In a first look, I have, let's say, 50 Hertz standard in my system. What is frequency range of usable signals? First answer 50. Digging a bit deeper, what is an operation range of ordinary equipment here? 49, 51. Wait, I can tell one thing. Steam turbines have setting. Steam turbine will perform emergency stop if frequency exceeds 52 Hertz. It's a normal setting for emergency shutdown. Low will be somewhere at 48. So, something like 48, 53 is reasonable. If we speak on steam turbines, if we speak on hydro turbines, typical rate for hydro turbine is from 10% of rated up to 120% of rated rotation speed. So if your device is intended to operate in hydropower, your possible frequency range should be extended up to 120% of rated frequency. For wind turbines, maybe up to 200%. It depends on design. Some of large turbine with kind of direct drive, synchronous machines, asynchronous machines, large scale, they are not so tolerant to high rotation frequencies. Some allow, if we have inverter in middle in the this power supply up to 200%. For kind smaller devices can operate at higher frequency. Usually large high power devices are not tolerating wide frequency shift. But that's not all. Basic algorithms rely on 50 Hertz on basic frequency. Basic. If you speak on Earth, start to speak about Earth fault protection, it often uses 150 Hertz components. Here frequency range should be above 150. One more moment. Protection devices with sense of current transformer saturation. Such kind of device usually need 5 ohms, 250 Hertz. So typical usable signal range is somewhere 300, 350. Sometimes 7th harmonic also used. Cut off. On the other hand, where this cut off line in analog preprocessing should be. If we, for example, this device, it has sampling rate 1 kilohertz. Sampling interval 1 millisecond. Signal at input should not contain components with frequency above 500 Hz. It's a must. So it should cut its input. Preprocessing part should cut everything with frequency above 500 Hz. Or something bad may happen. Use. This is, how to say, useless. Okay. How can I do it? At the first look, I can use something like this. This is ground. X. Okay. UX. UY. Output. Simplest circuit I can use. Can I write for simple, for example, it's powered from simple AC source with frequency omega. What is output will be input multiplied by 1 divided by omega c and R plus 1 divided omega c. Is it correct? Really? No, yes, it's correct. 1 plus J omega RC. What is a body plot?
What LS and all? LS every time and different colors.
My friend is working in colors. We told me that
They're hiring.
they're high, but they can.
They will give work permit also.
No,
Yeah.
tell us.
Tell us. Yes.
He's taking. He told me that they will take these people and they will.
Send some errors.
No. Fire. They will fire the group of people immediately or suddenly without any pepper. Tell me like that.
Without any exam test. Yeah, I haven't also got test. I have applied it.
You have applied it.
They are sending me back for team manager
No?
application.
What happened?
Nothing. I don't have experience for team manager. I applied for customer support.
But they
Yeah,
send
no,
you
no.
the
I have
team
also
manager.
applied for team manager also. Maka, let's see what's going on. But I know I'm not. They're asking for experience, so there's nothing. But like they reverted for it, but they didn't revert it for customer support application. That's what I'm saying. And they also have something now, AI something, and they also reverted. I have got it test.
How was that?
I haven't done it. I got it day before yesterday evening, so I haven't done it yet. It's a freelancing job from them, but it's nothing big. It's just a money. It's not on the work.
I'm sure that if we pass from here and we will get a job in the algebra field. I don't think so.
Obviously, nothing. We don't know any shit about this, man. Have we touched it anything? Have we ever? We are now studying engineering for 6 years, right? And have you ever hold a tester? Have your teacher ever told like this, that capacitor and that resistance really look like this, and this is the way it current? No, not at all, man.
Even though if we have the knowledge, I don't think so. we will
Yeah,
be
there
able
is
to do.
nothing. Yeah. And this electrical is so wastage because this also doesn't make our mind to learn this languages, skills and all, right? If we go into computer science and then it get us in more languages. Okay.
So, what is a motherboard? Oh, you have completed electronics. Take a look. Output is input multiplied by 1 plus omega Rc. Correct? Correct.
Not very good.
Yeah?
It's very good.
Nothing good here. Output voltage is input voltage multiplied by 1, why am I writing R? I should write 1 plus your omega Rc. Yeah? Yeah. I can do what? I can write output voltage is input voltage multiplied by what's this? Is it dependent on voltage? No, it's only dependent on frequency. So it's a kind of function of frequency, and because I'm using this beloved square root from -1, it's a complex. So it's a function of complex frequency, and it's called transfer function.
That's iota?
Transfer function.
You mean that's iota, right?
Yeah, it's a square root from -1. It's a function of complex frequency. So, border plot is a magnitude of transfer function as a function of frequency. We'll see something like this. Appears you're not believing me. So, this circuit suppresses high frequencies and passes through can achieve coil also will act as a low pass filter. Low pass filter passes low frequency and suppresses high frequency. In this line can be well approximated with a straight. You often will see in literature, if you will look in literature, 6 decibel per octave. What does this mean? What's a decibel? Decibel is an ratio. It's a notation for ratio. Something in decibel will be 200 decimal logarithms of, let's say, x2 to x1. 6 decibel is approximately twice. Octave, within 1 octave, frequency changes 2 times. So 6 decibel per octave means what if you increase frequency twice, output will drop also twice. Nice tiny low pass filter. For many applications, such filter is sufficient. Where here should be somewhere. Oh, yeah, here they are. Input board of device. Resistors and capacitors. Set resistor, capacitor, plus DC. Minus DC. 15 volt plus 15 minus 15 volts. Analog ground. Simple low pass filter with these blocks are diodes matrix with simple over voltage protection. For simple device is okay. But not life isn't always so simple. For more precise device, there may be a problem. Problem number one, the slow, so 6 decibel per octave is quite slow. This may be not insufficient. In theory, we can connect multiple XC, how to say, cells in series to obtain 2 of them will give us 12 decibel per octave. But that's not all bad news. Bad news if we need a truly high sensitivity, we may need band pass filter. We may need to to suppress low frequency part of the spectrum too. Most who face this problem is protection units for high end generators. They made quite high requirements on precision and sensitivity on one side, and on the other side they are fighting with effect from outer transients. Problem is what with digital. At the point we perform digital processing, not always possible to suppress so-called side lobes outside. So pass-through frequency areas, we will speak about it. Outside of, how to say, information, this part what we need for, how to say, relevant part. So some designs to prevent misoperation in digital part require better filtering. They require cut from the whole spectrum and high device of high precision, highly sensitive device, put precision cap, how to say, put a cap on error. One of the problem such simple filter capacitors do have drift in their capacity from temperature. It brings in precision, but more problem, real problem when you need uniform performance in frequency range without distortion. Both the problems, such kind of low pass filter brings angular shift also. Yes, it brings angular shift. It's not always allowed. Some device designs inherited from Analogue had narrow band pass filters based on resonance circuit. In general, if needed, input 1, omega 0,1 equals to omega 0,2 omega 0,1 square of AC. Two turned circuits, both turned in resonance. Without coupling, spectrum characteristic of such circuit, this one is for single circuit, peak at omega 0. By manipulating of coupling, it is for such system of two coupled circuits, it is possible to create characteristic like this. double. This part is adjustable by coupling. Well, it can be magnetic coupling. Some designs use capacitive coupling. It's expensive and nowadays it's a rarity. It's an old style design. Problem with manufacturing of this of such coil, it's quite expensive thing. Such design isn't in modern devices. Such design is very rare, and it intended for when used, it's intended for earthfall protection of hydro generators. I don't know. Maybe in it should be something very unusual, but only case I knew, earthfall protection of hydro generators, large hydro generators, expensive. Most designs go simpler way. They try to avoid usage of coils, especially resonant coils. Expensive. Resonant coil is expensive. I can show filter unit, resonant filter unit with coils of 10 Henry. Not here. On my, it's away from my office. Custom made for communication wires. It can be open. Can I open it? One second.
No, not first 4 years, around 4, like say, don't go just after 2 p.m. to 7, 8, that's it. Like you will find rush, that's all. You will find machines free also, but like benches would be busy, which people do with tumble and all. So those are.
You will always go in the afternoon section.
I go anytime.
What about the after time? Oh, 11.
Everything is good. After 8 it's
Night time.
and before 3, 4 it's good. But yes,
Do you find like areas
but Polygo more of Naluka.
Numbers?
Verona has some good destruction, some really good songs. Good typing.
No, it's. I thought it's filter unit, but not. It's only. It's an amplifier.
Morning.
It's simple one amplifier. It was intended to use nice sealed coil for bandpass filter. Itself it contains no. Inside there is no.
For 12 months.
no filter inside. Okay, where we are? I need to go forward.
Using second one.
Seal field. Useless.
Then we have this stuff. And it's doing after thesis. This stuff.
Other one, two subjects.
They are only 3 classes and one has thesis classes.
No, only 3 classes. One is that online is taking. One is this.
And one is with that alone.
Yes, I think.
Okay.
Optimization of it.
Even have also have some one of them. But I must but exams
Okay.
Yes, I think. It is like the normal subject.
Let's say we have elementary low pass filter. Ground? Its transfer function. Hmm? 1 divided by 1 plus omega fc. Simple. In Laplacian space, if we use Laplacian frequency c plus your omega, what is Laplacian space? Who know about Laplace transform? Laplace transform. Common form of Fourier transform. You have theory of signal completed. See. Okay. Laplacian transform is a common form of Fourier transform, and its operators with complex frequency c plus j omega, where c is a real constant. And so, transfer function in Laplacian space will be 1 divided 1 plus p Lc. Usually, to draw charts, so-called normal frequency is used, being real frequency divided by some kind of base or ground frequency. Knee point of the filter. Knee point. F got is 1 divided by double P FC. In this point, PFC and transfer function will be 1 divided 1 plus Pn. Fine. If you like to draw a nice chart, nice body diagram, square is 1 divided 1 plus omega n square. So, if your normal frequency is greater than 1, meaning what f is above knee point, your transfer function will become 1 divided by frequency, so it will drop down 6 decibel per octave or 20 decibel per decade. So if frequency increases 10 times, output will drop also 10 times. You can use multiple filters in sequence. You can use multiple LPFs in sequence. Blah, blah, blah. In such case, transfer function as a function of normal frequency will become 1 divided by 1 plus alpha 1 what I'm doing, Pn 1 plus alpha 2 Pn blah 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 1 plus alpha n Pn. With all this alpha 1 alpha are greater than 0, are positive and real. We have set of positive and real factors. So, for normal frequency much above 1, we will have transfer function dropping down approximately with rate approximately 1 divided by this normal frequency in power n. Really, your transfer function will go down with a rate number of filters multiplied by 20 decibel per decade. Interesting, but this transfer function will have also n negative real roots. If all cells are equal, if all cells are equal, So alpha 1 equals to alpha 2 equals to alpha n. You have all cells equal. You will get what? You will get square root power n from 2 minus 1. This is critical decay of our filter. In this case, each of the filter will have its key point, common filter key point multiplied by 1 divided by alpha. In common form, transfer function of this multi-cell Lopez filter can be written as zero one plus C one Pn plus C2 Pn squared plus C3 Pn power 3 plus blah blah plus Cn Pn power n. Here, all C1, Cn are real factors. So, imaginary part of Ci, where I changes from 1 to n equals to 0, they all are real, and that's not all. C1, all Ci, I starting from 1 to n are greater than 0. So they are all positive and real. If it is possible to take this polynomial and represent it as a multiplication, so factorize it. So if we can factorize it, this will work, this will correspond to real existing network, so feasible network that can be created. If you started to create your nice frequency chart and got complex roots, it's a problem. Complex roots means what there is no warranty what you will create this filter. Because factorization of high rank polynomials isn't an easy task, sometimes it's easier to work with plus alpha 1 Pn plus P1 Pn square multiplied by 1 plus alpha 2 Pn plus alpha 2 sorry, no, it's chaos. If I use alpha, here should be beta. Alpha 1, beta 1, and this one will be beta 2 Pn square multiplied blah 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 square. Some design ideas use decomposition into square quadratic equations. All alphas and betas are real and positives. Each idea, each designer may require its own filter optimized. Sometimes optimized means what we will get truly optimized filter may require, you know what? These alphas and betas may become complex and conjugated. Complex conjugated. Who remember what means conjugated? If you have, for example, x a plus dot b, its mirror will be L minus dot b. So when you try to design optimal filter, optimal analog path for your signal, you may get as a solution pair of complex conjugated roots. Such filter it cannot be passive, but with addition of amplifier, especially kind of see when your input part is transformer, this input transducer is transformer, which can be loaded. There is no problem of energy consumption in this preprocessing part. If you deal with something with low load capability, like Rogovsky coil or small size air gap transformers, you don't have load capability. This means that you need to compensate, you cannot use signal energy in filter. So this means that you will need active.
You have jet lag.
You slept well.
You have jet lag.
Meaning, what is meaning?
For unlimited range time.
What I will tell you need to compensate energy loss. It means that your filter should contain amplifier. Yeah? Should be active. Operation amplifiers. You will have electronics mark in your curriculum. You don't know what operation amplifier is? Op-amp. Yeah? So your input, this part which will perform analog preprocessing, should be active. You should think pair of op-amps and maybe not pair. If you have 12 or 15 channels, you will have set of active. Some do this device designed in interesting. It has first passive filters but it has transformer input. And then multiplexing, this point is multiplexer switch. And active part or pump with one for all channels, it's switchable. More, it's not the, how to say, it's a budget design. If you deal with high-end generator protection or high-end phone location, budget will be. And you can allow active filter for each channel, tunable. This one has set of passive filter and only one or pump for all the switchable model. So what's good in switchable model? It's cheap. What's bad in switchable model? What's bad? Where the dog is digging? Where's the problem with switchable filter serving all channels one by one? You need to wait for transients to end. You have a set time of all this. You switch to channel and you have to wait until transient ends. Only then you can measure. Then you switch to next channel and again you have to wait. This downgrades your performance. You cannot. Okay, if your system you work so you have this time for setting, but if you need higher levels of performance, this will not work. Okay. One problem. Your system will have complex rule. One more. Again. Coils for high frequency are available. Coils for low frequency also are available, but for mammoth price. Real manufacturing don't like coils with high inductance. When you need something 5 Henry, 10 Henry. Hey. Stop using this drug. Stop. Please. They are at the top levels of components expanding. So it's better to avoid expensive components. There is a mass base inside of polynomial mass base for best filter possible. There are several classes of filters best possible. Number one is a Butterworth based design. So number one is a Butterworth. Butterworth filter, filter based on Butterworth design, will offer you what? Long horizontal path and fast decay. Butterworth filter faster will have something like this, long horizontal path and fast frequency magnitude of transfer function. But there is one problem with Butterworth filter that works very fine when you deal with stationary repeats. Problem, transient characteristic of Butterworth filter. If you need to deal with transients, Butterworth filters it's transient, its reaction to transient will be like this. For comparison with critical decay, white is a Butterworth, red, something like this will be simple RC filter. Another one is a Chebyshev filter. Chebyshev's polynomials are polynomials with minimal distance from 1. Chebyshev's filter kind of wavy and then very fast. Chebyshev filter gives a very sharp cutoff, but Chebyshev filter based on Chebyshev polynomials, have oscillations, kind of waves in its passing along. If we deal with narrow frequency range, for example, 50 Hz and 1 plus minus 1, Chebyshev filter may be what we need, because it sharply cuts high frequencies. But if we need wider range, Chebyshev maybe not the best solution. Chebyshev filter on transients oscillates like hell. High rank Chebyshev filters are performing nicely on transients. If you need to deal with transients, your best solution is a Bessel filter. Bessel polynomials can be used to create very good filter. But it's here at cutoff Bessel filter isn't the best. Usually, you cannot there is no silver bullet. There is no silver bullet for filter. If you need good suppression of higher frequencies and in narrow frequency band, you operate a narrow frequency band, Chebyshev is good. If you need good performance on transient, Bessel is your choice. Bessel. If you need uniform performance in wider operation range, you look for Butterworth. Okay, maybe Okay, Butterworth filter for Butterworth filters. Equals to h0 squared divided by 1 plus k omega and square plus this one is number 2, number 4 omega square plus k double n omega n power double n. Butterworth design use only odd frequencies. Since what там square can be approximately written as h0 squared divided 1 plus chi n omega n power double n. Since higher frequencies do, how to say, take a higher role in divider. Because we know what at norming frequency filter decay should be 1 per each free. It's about. We can write what h0 squared divided by half equals to h0 divided by half 1 plus k double n. So should be 1. For Butterworth filter of nth order, for Butterworth filter for n order, should be h0 squared 1 plus omega n power double n. So we need a schematic performing this way. To get true, we don't actually, to create schematic, we cannot use square of model. We need complex because we need also phase shift. If we write the situation, we will get Butterworth polynomial For first order Butterworth polynomial give us one plus normed frequency. For second order 1 plus square root of normed frequency plus normed frequency squared. For third order 1 plus 2 and plus double normed frequency square plus normed frequency this can be rewritten as 1 plus normed frequency, 1 plus normed frequency plus normed frequency squared. And so on. For example, for fourth order will be 1 plus 1 8 4 8 pn plus pn square multiplied by 1 plus 0.765 normed frequency plus normed frequency squared, and so on. Actual poles of transfer characteristics we can get closed form. It's not a giant problem. So we can get for odd and double E blah 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 double cosinus double I minus 1 divided by double n p. This is for I starting from 1 and up to n by half. N is order. For them should be 1. For even, for cases of even n, will be double cosine I minus 1 p divided by double n I starting from 2 and ending by n plus 1 by half. Bi is 1. Low and polynomials are family, the higher n, something like n1, but high rank. High order Butterworth filters, which, so this word on transients, they have for, just to understand, for second order n2, this second overshoot will be 2.3%. For n10, overshoot 17.8. For n10, this overshoot will be 17.8%. But really, if you're looking for analog preprocessing, it's straight and equal and nice line in all your operation frequency zone, you will choose Butterworth filters. In reality, there are plenty of fitting programs. You just ask for Butterworth filter design, and this thing will help you. You just set knee point and order, and this thing will create you. Because they are very popular in acoustic processing. Okay, I don't have time. Next time I will draw Chebyshev and Silent Kid. Butterworth offers us nice line at operation range and fast drop. What's good? It's uniform. In frequency shift, we can be sure that in case of frequency shift, our preprocessing part will not disturb us. And it offers good cutoff. This simple design means, it had error 20-25% for fifth harmonics. The simple design RC worked on 50 Hz, but when we needed 250, error was above 20%. Not the best design. Honestly, it's a cheap. If you when you need fifth harmonic, it's a good indicator of current transformer saturation. Okay, I will stop for